In this problem, we solve the rational equality 3x squared plus 13x plus 9 divided by x plus 2 squared. All that is less than or equal to 3. So we're going to find all the real numbers we can put in for x on the left-hand side so that the left-hand side is less than or equal to 3. So the first step is to rewrite the inequality so that 0 is on the right-hand side and the left-hand side is a single quotient, a single fraction. So to do that, the first thing we do is subtract 3 from both sides, and then we have to rewrite the left-hand side with a common denominator. Well, the common denominator is x plus 2 squared, and so we can rewrite minus 3 as minus 3 times x plus 2 squared over x plus 2 squared. In the numerator, when we expand x plus 2 squared, we get x squared plus 4x plus 4. And then when we combine the numerators over the common denominator, we get the left-hand side simplifies to x minus 3 over x plus 2 squared, and that's less than or equal to 0. That is an equivalent inequality. The solution to that inequality is the solution to our original inequality. So we're going to find all the real numbers we can put in for x so that the left-hand side, x minus 3 over x plus 2 squared, is less than or equal to 0. So in step 2, we got to find all the values of x for which the rational expression on the left is equal to 0, and find all the values of x for which the rational expression on the left is undefined. Well, the rational expression is equal to 0 for those values of x that make the numerator equal to 0 and the denominator is non-zero. So we set the numerator x minus 3 equal to 0, and when we solve for x, we get x equals 3. So x equals 3 will make the rational expression equal to 0. To find the values of x that make the rational expression undefined, we set the denominator equal to 0. So we set x plus 2 quantity squared equal to 0, and when we solve for x, we get x is equal to minus 2. So x equals 3 makes the rational expression equal to 0. X equals minus 2 makes the rational expression undefined. So in step 3, we plot the numbers minus 2 and 3 on the real number line. We know that minus 2 makes the rational expression undefined, so it is not in our solution set, so we put an open circle on minus 2. At 3, we know that it makes the left-hand side equal to 0, and so we put a closed circle on the number 3. Now we have 3 open intervals, right? Those two numbers divide the real number line into 3 intervals, and we have to determine whether the numbers in any of those 3 intervals is in our solution set. So in step 4, the first interval consists of all real numbers less than minus 2. The second interval consists of all the real numbers between minus 2 and 3. And the third interval consists of all real numbers greater than 3. So in the first interval, from minus infinity to minus 2, I use minus 3 as my test point. And when I put in minus 3 into the rational expression, the numerator is negative and the denominator is positive. So we have negative over positive, which is negative. And so any real number less than minus 2 will make the left-hand side of our inequality less than 0. And so those numbers work. Any real numbers less than minus 2 will be in our solution set. And down below the table, you can see where I've shaded in on the real number line all the real numbers less than minus 2. For numbers between -2 and 3, I use 0 as my test point, and when I plug in 0 into the rational expression, the numerator is negative, the denominator is positive, negative over positive is negative, and so all those numbers work between -2 and 3. Any real number greater than -2 and less than 3 put into the inequality in step 1 will make the left-hand side less than 0. So those numbers work, and so I have shaded in those numbers in the number line below the table between 2 and 3. Lastly, we have the real numbers greater than 3. I use 4 as my test point, and when I put 4 in for x in a rational expression, the numerator is positive, the denominator is positive, positive over positive is positive, and so any real number greater than 3 put into the rational expression will make the left-hand side less than greater than 0, and so those numbers don't work. So the numbers greater than 3 are not shaded to the right of 3 on the real number line below the table. So the only numbers that satisfy our original rational inequality and the equivalent inequality in step 1 are the real numbers less than -2 and the real numbers greater than -2 and less than or equal to 3. And so I have the solution written there in step 5 in interval notation.